In the previous lecture, we just learned how to calculate the equilibrium constant, which
has the symbol K. It also has a symbol Kc, because Kc there stands for concentration, and sometimes you'll see it written as Keq. So all of those refer to that same
mathematical expression of concentration ratios.
The magnitude of K actually tells us something about this reaction. So you can see that
K is a ratio of product concentrations to reactant concentrations.
Products on the numerator and reactants in the denominator. That means that if the value of K is really large, so much bigger than 1, that tells us that there must be a lot of product and very little reactant
at equilibrium.
We would say that when the K is much larger than 1, that the equilibrium will lie to the right, which just means that it's very much on the product side and favors the product, okay? The opposite situation when K is very small, which just means it's between 0 and 1, but much smaller than 1, let's say 10 to the minus 10, for example, K cannot be negative, right? It's not a negative number. Then the equilibrium will lie to the left, or it favors the reactant. So in this context, again, in terms of reversible reaction, we always refer to left as reactant and right as product. Okay, so you'll see sometimes we'll say, does it favor the left side or the right side? That just means, does it favor reactant or product, okay?
We also have to define what we mean by small and large. We can use this rule of thumb.
If it's greater than 10, we can say it's greater than 1. If it's less than 0.1, then we can say it's less than 1. Now, what about a number between 0.1 and 10? That's when the K, we would say, roughly is equal to 1, which just means that the ratio of reactant and product are about the same.
Which just means the reaction doesn't favor one side or the other. Now I want to discuss the unit of K.
When you calculate K, you might think that, well, we have all these concentrations, so the unit should be some kind of molar raised to some power. It turns out that K is unitless, and let me explain a little bit why that is. The reason is because we find that in aqueous solution, which is when we calculate concentration, right, we're taking the value of the number of moles of solute divided by the volume of solution. This really assumes that you have your solute, like an ion, for example, just surrounded by a bunch of water molecule. It turns out that that's not true. So this is what an actual ion looks like in solution. It's shown in the picture on the left. You actually have
the yellow cation here,
surrounded by water, but it also has some of these anions still surrounding that cation. So it's not completely independent of the anion. So some of the anions are kind of stuck around this cation. Similarly, when you look at the anion, some cations are stuck around it with a bunch of water surrounding those as well.
The reason this matters is because
if some of these anions, these green ions, are surrounding the cation, that means that they're not freely floating in solution. They're not freely floating in solution. Then we have overestimate the number of ions that are
in solution,
because some of the ions are actually stuck together with the cation. Similar situations happen here with the cations. They're kind of stuck together with that anion. So as a result, we have two different concentrations that we really need to look at. The first one is what we call the stoichiometric concentration or molarity. This is the stuff that we've been calculating, Chem 11, Chem 10, right? We just assume here that all the ions separate and they're all just surrounded by water. This is true only for
dilute solutions. Although we use dilute solutions in many experiments, we also work with solutions that are higher in concentration where we cannot use molarity to measure its concentration. Here we use another measure called
the effective concentration. This is also called activity. Okay, so it's different than molarity. It has symbol A as opposed to M, right? This is the actual concentration, and that actual concentration is lower than the molarity. Why? Because of these ion effects that I just mentioned to you, okay? Because of that, if we want to calculate the equilibrium constant, in reality, what we should use is not molarity.
We should use
activity. We should say the activity of C raised to the power of C, and then the activity of D raised to the power of D, etc. Okay? And that's the expression that's shown right here. But when we calculate using activity, we have to have a standard reference value to compare the activity to, because we need to know what is the limit when there's no interionic interaction. So that number is given as 1. And so because you're dividing both the concentration unit in molarity divided by the standard concentration, what ends up happening is there's no unit because the units cancel out already. So in the end, the K has no unit at all. If you don't understand this idea of activity versus molarity, it's okay, but the only thing you have to keep in mind is that when you calculate your K,
just make sure it's unitless.
Okay, so we just talked about that idea of the equilibrium constant, which again for a reaction given there at the top, which is AA goes to CC and DD, the equilibrium constant is just the ratio of the product concentration at equilibrium raised to their coefficients divided by the reactant concentration at equilibrium raised to their coefficient. Remember when we were talking about kinetics, we had said that when we measure rates, we also have something called the rate constant. Turns out the two constants are related to each other, and this is best observed and derived for elementary reactions. So if you think about elementary reaction, let's say I have a reaction that looks like this. Okay, AA goes to BB. It's a reversible reaction, and there is forward rate, call it KF, and there's the reverse rate for the reverse reaction, call it KR. This is the rate constant, okay? And so let's write the equation for the forward rate, which is just going to be rate equals KF, since that's the rate constant, times concentration of A raised to the power of little a, its coefficient. And why are we allowed
to use the coefficients as order?
Because it's an elementary reaction. Let's talk about the reverse rate. That will just be rate equals to KR times B raised to the power of little b. Now, what happens at equilibrium? We know that forward rate equal to the reverse rate. If that's the case, that means that KF times A to the A should equal to KR times concentration of B to the coefficient. Now, let's rearrange this a little bit where we bring the concentrations to one side, bring the rate constants to the other side. So we can write it as KF over KR equals to B to the power of B over A to the power of A. Now, at equilibrium, these concentrations are equilibrium concentration. That ratio is the same as the equilibrium constant, isn't it? Same as KQ, right? Because it's the ratio of product over reactant, both raise their coefficient. So that just tells you that ratio of the rate constant, forward over reverse, is the same as the equilibrium constant of that elementary reaction. Again, assuming that we are doing this at equilibrium, so we're using that equilibrium concentration. That relationship is quite useful because then we can use it to calculate one of the constants if we need to. Now, this works not just for one step, but it works for multiple steps as well. You can show that the equilibrium constant is the same as the product of multiple ratio of rate constants. Each one of them is the forward over reverse. So this is the forward over reverse rate constant for step 1, forward reverse rate constant for step 2, and keep going until you have step n. And if you multiply all of them together, you get the equilibrium constant. Okay, now let's take a look at how equilibrium constant expression change as a function of the state of matter that we're dealing with. So we're going to first talk about what we call homogeneous equilibrium, which is just equilibrium where
all the species are in the same phase.
So this applies to when they're all in aqueous phase, like in this reaction right here, or when they're all in gaseous phase, which is like this reaction right here. So for aqueous species, the K is simply just the ratio of molar concentration as we've seen before. So if you have a reaction like this, where you have nitrous acid breaking apart into a proton and the nitrite ion, the Kc expression is just that, right? It's the product proton raised to the first power times the nitrite ion raised to the first power divided by nitrous acid concentration at equilibrium. If you have gas species, the K can be your molar concentration expression, or it could also be ratio of partial pressure because it's a lot easier to measure pressure of gases. So when you have gases like this, you'll see that they give you something called Kp, which just means it's the equilibrium constant expressed in ratio of pressure. That's why the letter P is there. And so it's the pressure at equilibrium of the product raised to the coefficient, so in this case PnO2 at equilibrium squared divided by P of N2O4
at equilibrium.
Okay, raised to the power of 1, so it's just the number itself. Now, of course, it turns out Kp and Kc are related to each other because of the ideal gas equation, which is PV equals nRT. So P, which is pressure, is N over V times RT. What is N over V? Well, that is just concentration, right? So in other words, P is equal to concentration times RT. You can actually derive an expression, which is shown right here, where Kp, once you relate it to concentration, will just be equal to Kc times RT, gas constant times temperature in Kelvin, raised to the power of delta N. So delta N is just the sum of
all the gas product coefficient minus
the sum of all the reactant coefficient, okay? And this applies only to gas, so we're only taking the gaseous species in the reaction. You can see that the final equation is just that. Kp equals Kc RT to the power of delta N. Now the R here that we use is this R, 0.0821, because we're talking about pressure volume relationship, so we have to use that value, not the energy value of the gas constant. So let me show you an example of how to apply this. We have here a reaction. This is a homogeneous equilibrium. They're all gases there. 2NO plus O2 goes to 2NO2. They tell you that at equilibrium, they have the following concentrations for NO, O2, and NO2. And then they want to calculate Kc and Kp of the reaction at this temperature, which is 230 Celsius. The Kc expression should be hopefully pretty easy to see. The reaction is this, right, at the top. So the Kc expression should just be this expression right here. Product squared over NO squared times O2, okay? Plug in all the numbers we're given because they're all equilibrium concentrations already. We get this number 6.44 times 10 to the 5th as our Kc. Now, first thing you should think about is, remember our interpretation of Kc values earlier. This is a reaction that is favoring product.
It's a product favored reaction because
value is pretty big, much bigger than 1. Now let's calculate the Kp.
Just use the formula between Kc and Kp,
which is Kp equals to Kc times RT to the power of delta N. So the delta N is just the sum of the coefficient of the product gas, which is just only one product and it's 2. And then the sum of the reactant. Well, there's 2 reactant gases. They're 2 plus 1, so it becomes 3. So 2 minus 3 equals -1. So therefore, RT to the power of -1, something to the power of -1 is the same as 1 over that number. So that's why I have Kp equals to Kc over RT. And then I use the Kc value I got. This is my R. This is my temperature, but it has to be Kelvin. So I add the 273 to make that conversion. I have a final answer of 1.56 times 10 to the 4 as my Kp value. Now let's take a look at a second type of equilibrium with regards to phases, which we call heterogeneous equilibrium. And this refers to when you have a reversible reaction that has reached equilibrium where you have species in different phases. So some of them are aqueous, some of them may be solid, some of them may be liquids, and some of them may be gas. In that situation, as in the example shown right here, how would you write the equilibrium constant? Well, it turns out that if you think about it, the concentration of a solid or a liquid
is proportional to
its density, right? So if you think about what concentration is the number of moles over volume of the solution. But then in this case, if it's just a solid on its own, there's just the volume of the solid. The number of moles will just be the number of particles of solid, which is proportional to its mass, right? Because you can convert that to mass. So this number is really very similar to density, and density doesn't change. So in other words, the concentration of a solid or a liquid are both constant. Because they're constant, they don't really change as the reaction progresses, right? Doesn't mean that the reaction doesn't require the presence of the solid, right? You have a reaction, and let's say you have a lot of solid at the beginning, and then the reaction progresses, and then you have less solid at equilibrium. So the reaction uses a solid, but the concentration, okay, of the solid, which is again the number of moles over its volume, is constant. It's the same number there as it is here. As a result, when we have a reaction like the one I'm showing right here, where we have a solid, and then a gas, all we put in our K expression is just the gas, because that's the one where the concentration would actually change because you're dividing number of particles of gas over the volume of the container. So here's the actual K expression for that reaction, okay? So it's just the gas that you're expressing because that's the only one where the concentration actually changes over time. The Kp expression, of course, would just be the pressure of CO2. Here's a quick example of a reaction that has both solid and gas and liquid in it. And you can see here that the K expression then would just be something over the gas concentration. That something should be 1. So even though you have nothing there, it's just 1, because remember what I just said about activity, it actually has an activity of 1 divided by the solid doesn't factor in. And then the gas would be Cl2, concentration raised to the 6th power in this case.